Now it's my pleasure to introduce the next speaker, which is Jean-Pierre Merlet from INRIA Sofia Antipolis, where he's running the Hephaistos project. Jean-Pierre is an IEEE fellow, Dr. honoris causa at University of Innsbruck, interested in control theory, interesting parallels to artificial intelligence, mechanical engineering, mathematics, computer science, and he will tell us about some of his work on all of those topics today. Can you share your screen?
I am sharing my screen, and thank you for the nice introduction. I hope everybody is hearing me. So my talk will be about designing system using a methodology which is called appropriate design, and this methodology will be illustrated on the example of parallel robots. So in system design, the objective is to design a system whose input-output functions satisfy a minima a set of performance criterion. There are two steps in system design. First one is synthesis design, and second one will be dimensional design. In synthesis design, we have to determine a global structure for the system. I call that its topology, that seems to be convenient for the task at hand. So it's just a global structure, an arrangement of joints and so on. And if you want to build a physical instance of the chosen structure, then you have to determine some nominal values for a set of parameters that will allow you to build the system. In the dimensional design step, the objective is to determine set of nominal values for these parameters, for this set of parameters, so that the physical instance of the system obtained with this value will satisfy the set of performance criterion. In this talk, I will focus only on dimensional design. I will not address the problem of synthesis design. So let's give me some example of some robots we have designed using the approach I will talk about. On the left side, you have automatic stuttering robots based on a parallel robot called the left hand. In the middle, on the top line, you have a 6 degrees of freedom robot used for assembly tasks because it's very accurate. The third image is a very small 3 degrees of freedom endoscope whose diameter is 7 millimeter. At the bottom on the left, you have systems that we have designed for the European synchrotron radiation facility, and the device you see on top of the robot is a specific mirror used to deflect X-ray with a positioning accuracy which is about less than 1 microradian for the orientation. And the last image is a wire-driven, cable-driven parallel robots, 3 degrees of freedom. The moving part is basically this drum, which is containing some glass powders, which are used for artistic exhibition, for example, writing on the ground, the logo of INRIA. It is actuated by these 4 cables with a high accuracy and also a very high payload, which is here about 150 kilogram. And this system is also used to assist elderly and frail people to stand up, to walk in an automatic way. So what kind of parameters do we have in a system? I will say in a robot. We have geometrical parameters, strokes of the linear actuators. If we have material parameters, for example, for the cable, we have the Young modulus of the cables. We have kinetics and dynamics parameters, for example, actuator speeds and acceleration. We have static criteria, force in the legs. We have also constraint parameter coming from the computation we are using, for example, the sampling time. We have parameters coming from their sensors, what is the range, what is the type. And performances we are interested in is basically workspace, which is very important in system design, robot design. We have accuracy, we have speed acceleration, maximum load, and so on. There is some difficulties in system design because the performance criterion we are considering are very different. They have different units, they have different physical meanings. Furthermore, some performances may be antagonistic. For example, workspace versus accuracy is antagonistic. If you want a robot having a very large workspace, then you cannot expect it to be as well very accurate. So you have to make some kind of compromise between these two performances criterion. Another very difficult problem is that the real parameters of the physical instance, the robot you will have built, will differ from their nominal values because of the uncertainties in the manufacturing, meaning that the performances of the real instance will differ from the performances of the theoretical robots. A classical approach in system design is the cost function approach. Basically, for each requirement you define, well, you try to define a numerical index, let's say in the range between 0 and 1, which is the larger it is, the better the performance required is fulfilled. Then you construct a cost function, which is basically a weighted sum of all these numerical indexes, where you put some weight because you have different units and you have different priority in the requirement. And then you use a numerical optimization procedure to find the value of the parameters that maximize this cost function. But there are a lot of drawbacks to this approach. Is there an optimal design? No. No, we don't, as soon as we have antagonistic requirements. And we will always have antagonistic requirements. So we have just Pareto optimal design. Then other drawbacks is the definition of the index. So for example, it's maybe quite complex to define an index relating to the workspace shape. We need also to be able to compute very quickly all these indexes because the maximization process will require a large number of the cost function evaluation. It's a computer intensive approach as soon as the number of parameters is large. And a major drawback is that this approach does not allow to manage uncertainty, which are unavoidable. So the theoretical design we may get with this approach may be satisfactory, but it will not be true for the physical instance that we will construct based on this theoretical robot. The weight. Well, we have different units. So for example, for our workspace, we have cubic meters, while we have Newton for legs, tension, or forces. So if you put weight, it's basically because you have different units, but the choice of the weight is completely arbitrary. You just decide that 1 Newton is exactly equal to 1 cubic meter, for example. So it's very arbitrary. And the design you will get is very sensitive to all this weight. And there is a theorem, a nice theorem, that shows that there is no single set of weights that will allow to find all Pareto solution if the constraints you have are not convex. And most of the time they are not convex. So there are other optimal design approaches, basically physical programming, target casting, but they have all the same drawbacks in the cost function approach. We may look at artificial intelligence method, still work in progress. So I'm coming back now to the appropriate design motivation, which is basically to take uncertainty into account, including numerical round-off error. The motivation, the idea behind that is that in most design problems, we are not looking for an optimal solution. We are just looking for a solution that satisfies the requirements that have been given as inputs. An important point is that the design parameters and the uncertainties are bounded in general. So I introduced the parameter space, which is basically an n-dimensional space where n is the number of parameters, and one dimension of this space is associated to each to a specific parameter. So for example, for this robot, well, we have 3 design parameters: the diameter of the base, the diameter of the platform, and the angle between the 2 successive attachment points. Then we have a 3-dimensional parameter space So this point represents a unique design for this robot. And for a given requirement, only the point within a bounded region will satisfy the requirements. So the principle is we construct the parameter space, we consider each of the users and designers' requirement, SI, and find this region RY for which the requirement is satisfied. Then as soon as we have considered all requirements, here on the figure we have 3 requirements, we take only the intersection of these 3 regions and we get our design solution, an infinite set of design solutions because each point in the intersection satisfies all 3 requirements. To manage uncertainty, as soon as we have determined this RI region in the parameter space, we just shrink the obtained region by the tolerances we have on each of the parameters. So starting from this light green region, we shrink it by the delta, which are the parameters uncertainty, to get this dark green region, which is the region we will use for the design. So now the difficult point is calculating this region. In fact, I will go very quickly on that, but you can get an approximation of all this region by using what is called interval analysis, which is basically computing, instead of computing with real numbers, we compute with intervals values for the parameters so that we get for each function we are considering an interval value which include all possible value of the function for the parameters which are in the range. So basically, here is a result. It's only 3-dimensional. Also, the calculation was involving about 200 parameters, which is basically, we have the workspace requirement. We have considered 3 parameters, and this region in grays are the one which will satisfy the workspace requirements. We get the result, we get the region as a set of boxes. So if we have different requirements, then it's quite easy to compute the intersection of such volume because it's basically computing the intersection of boxes. Because of time, I will skip the algorithm part. What is the advantages of this approach? First, we don't determine a single design solution as we'll do the cost function approach, but we determine an approximation of all possible design solutions. This advantage approach allows one to deal with uncertainties, meaning that if we design and we choose a nominal value within the region we will calculate, then we are sure that the real system, which have uncertainties, will still satisfy all the requirements that we have installed at the input. It's computer intensive, but at the same time, it's quite easy to implement the approach in a distributed way, meaning that we may use several computers to decrease the computation time. And with this method, we are able to give to the end users various design compromises. For example, we have a solution with a large workspace, much larger than the required one, but an accuracy which is close to the minimal value given by the end users. Or at the opposite, we may have a solution whose workspace will be exactly equal to the one which is required, but with a very high accuracy. So I have 1 minute left. So conclusion, optimal design does not exist in general. In practice, doesn't exist. No, you are never focusing on the design of a system just to optimize one performances because you have several performances to consider. The cost function approach has a lot of drawbacks. It's still used, both in design, in control theory, a lot of stuff. But I argue that this is not a very good idea. It has so many drawbacks. Uncertainties. We cannot avoid them, but they are not taken into account in most design process. Also, they play an essential role on performances for the real system. The methodology we have been proposing and we have used for designing all of our prototypes, including the one, our own prototype, but also robot for companies, so-called appropriate design methodology, it's more realistic and allows to provide significant variety of compromises between all the design solution. It has drawbacks. It requires a strong analysis. You need a good system model, and it may be computer intensive, but it works in general. So 15 seconds left. So I guess I will stop there and we'll take any question if we have time.
Thank you. Thank you for the presentation. I have a virtual round of applause. Any questions? And please, attendees, type questions in the Q&A. Unfortunately, it looks like panelists cannot type in the Q&A, which is kind of an annoying lack of feature of Zoom. So panelists maybe type questions in chat, and then I will relay them to the audience. So any questions? So we have a question from the audience. It says, can the optimization algorithms with geometric search of the workspace perform better for mechanism optimizations?
Well, as soon as you have only geometrical parameters, it may be so, except that you will not be able to manage uncertainties unless you use interval analysis. Because interval analysis will give you a right answer, meaning you have a function and you want to have, let's say, the minimum of this function. And within this function, you have parameters which are unknowns, meaning that there is no one minimum value of a function. There is a global minimum. And interval analysis will allow you to determine this global minimum in a safe way, including, and this is very important, that is not well known by mechanical engineers, including taking into account numerical round of errors. It's not very well known, but our computers may calculate very badly. So for example, if you take the number 0.1, it does not exist in a computer, meaning that as soon as you are using this number, then you are sure that the result is wrong. With interval analysis, the round of errors are taken into account, and the result you will get will be completely safe.
And a follow-on question, does interval analysis suffer from overestimation?
Absolutely, that's clear. But there are a lot of methods which allow to decrease overestimation. And furthermore, basically interval analysis uses a branch and bound algorithm, meaning that as soon as we have overestimation, we'll decrease by 2 the size of the box and start again. And it can be shown that the size of the overestimation decrease with the width of the box, with the size of the box. And as soon as you go down in terms of width for the intervals, you can apply methods such as taking into account the derivative of the function with respect to the unknowns to get exact upper and lower bound for the function.
Got it. All right. Thank you once again for the presentation. Another
Thank you.
round of applause. And